You're given a piece of aluminum, and in aluminum there are 2.1 times 10 to the 29th conduction electrons per cubic meter. You're told that there's a current of 1 amp flowing, and it has a cross-sectional area of 10 to the minus 4 square meters. So here's our piece of aluminum with 1 amp flowing and our cross-sectional area. So the first thing we're asked to find is the magnitude of the current density. The current density is the number of amps flowing per unit area, so it's just the ratio of the current flowing to the cross-sectional area of the conductor, or 10 to the 4th amps per meter squared. In part B, we're asked to find the drift velocity of the conduction electrons for this current flowing of 1 amp, or this current density of 10 to the 4th amps per meter squared. We know that the current density is equal to the volume charge density of the conduction electrons times the velocity with which those electrons are drifting. And the volume charge density of the conduction electrons is the charge per electron times the number of electrons per unit volume. You're just asked to find the magnitude of the drift velocity. So for the current density, we put in 10 to the 4th amps per meter squared. For the charge on an electron, we put its magnitude, 1.6 times 10 to the minus 19th coulombs. In aluminum, there are 2.1 times 10 to the 29th conduction electrons per cubic meter. So we solve for the drift velocity. For units, we have amps times a meter over a coulomb, and amp is a coulomb per second, so this works out to meters per second, which works out to a drift velocity of 3 times 10 to the minus 7 meters per second. Recall that the thermal velocity at room temperature for electrons in a metal is about 10 to the 5th meters per second. So for even a hefty current density, the velocity, the drift velocity of the electrons are 12 orders of magnitude lower than the thermal velocity.